So here, just to show you, here we've been using random forest for classification. And just really briefly, you can also do random forest for regression. So here's a kind of an interesting model that I'm doing. Drawing 10 points between, or 100 points between 0 and 10. And then I'm creating a model that has a fast oscillation added to a slow oscillation and then some noise on it. So this is what climate data often looks like. And so this is the model right here. The blue points are the data, and this red point, this red is the fit to the data with the random forest classifier, or sorry, with the random forest regressor. So here we're saying we want, rather than classification, we want regression. We want the random forest to predict a continuous variable with 100 trees, and we're going to fit x and y and then predict, and we get out this model. So it just shows you that random forests are really, really flexible, non-parametric. So here we've almost perfectly fit this model, which is a large period plus a small period altogether. High frequency and low frequency, and random forest, that's it. So when you think random forest, think basically it's a non-parametric model. You don't need to tell it what the underlying function is, but it can usually learn that from data, even if the function is a really complicated thing. Yeah?
You, in real time, or not necessarily, make the low frequency, the high frequency sinusoid change in time and see what happens to the model that comes out?
Yeah, we can do that. So here's our fast oscillation. Instead of 5, let's make this 4 plus 0.2 times x. So that's our frequency. So that'll range from 4 to 6 as we go across. And we do that. Maybe I didn't do that quite enough. Let's do it. Let's make it vary more. 2 plus 0.8 times x. So here's our model getting faster, and actually, so this is not very well sampled by the data down here, which is probably why it's not catching it. But if we add more data points, let's make these 1,000 points instead. Did I do that right? Yeah. So now our random forest can actually get all those different frequencies. Now the trick is here, if you're trying to use this to determine the frequency, the trick is here you get, all you have is the way to, you have, as a function of x, the random forest gives you a y. It doesn't know that it's doing a frequency thing, right? So you'd still have to do something from the random forest where you're trying to determine from the model what this underlying frequency is.
What does the model look like?
No, it doesn't give you an equation. It gives you, it's exactly what we're saying. It's a set of trees, right? Where each tree says, given my value is, the first thing it says is, I'm going to split on, what are we looking at here? We're looking at x. So we're saying we're gonna split right here. And the first level, actually, we might be able to show this. Let's do this with max depth equals 1. Right? So we're saying each tree can only ask one question about the data. And just to make it clear, let's do just a single decision tree. That's not going to work. Oh yeah, we need the 1 there. So that's the number of estimators, 1. So if we just give it a single function, it's going to split on 6, and it's going to say everything less than 6 is here, and everything greater than 6 is there. Right? And then if we do 2 functions, it can split each of those again. If we do, 3 questions, it can split each of those again, and you start to see all this. And if we go all the way up to 10, then this is just a single decision tree. It can split all these, but you see all this noise that it's fitting, right? So that's why the single decision tree is not very good, because it's sensitive to the noise. But when we pump this up and average 100 decision trees, that noise gets, for the most part, averaged out, and you end up with this model. So it's really hard to interpret. Like if your model is just, what do we have here? We have 1,000 yes or no questions that we're asking of the data, and that's what makes this thing. Yeah?
Why not because in Sandra we just smoothing the data?
Smoothing the data? Yeah, you could do something similar, but it would be a different model. So it might be that the model would be that smoothing would be a better option in this case. But random forests are nice because they're non-parametric, and you might be able to get out some interesting insight if you do something like this. Maybe an open area of research. Yeah.
The questions combine different features. I mean, the values for different features. They are questions on individual features. Can you tell the question?
Yeah. So you're asking if you can basically if the split can be something different than vertical or horizontal. Yeah. So in theory you could do that, but that would make it a lot slower. One of the reasons random forests are so useful is because it's incredibly fast to just do these vertical or horizontal cuts. And yeah, you could do some combination. You could try to do a PCA on your data and rotate it and try to find a more optimal cut. But that would cost a lot. It would be really computationally expensive. And in practice, it doesn't actually buy you much because anything you can do with one diagonal cut, you can do with 4 or 5 horizontal and vertical cuts. And once you do the random forest, you kind of average out those jagged edges, and you end up with something that looks more curved in effect. So yeah, the reason people like random forests is because they're incredibly fast. You can throw 1 trillion points at this, and you can do something reasonable with that. Whereas other methods, if you try to do some sort of filtering or smoothing, that might be more principled to go that way, but it would be really, really slow in comparison.